So once we know that, like I said, we can use this fact to build other ideas or theorems regarding triangles. Okay, so we'll give you a couple definitions here. First one is an acute angle is one that is less than 90 degrees. A right angle is one that is equal to 90 degrees. And finally, an obtuse angle is one that is greater than 90 degrees. Now, with these definitions and the fact that the sum of three angles cannot be greater than 180, we have some restraints on the angles of a triangle. For instance, let's take the right angles for a moment. I cannot have two right angles in a triangle. If I did, right angles are 90 degrees, so this, let's say A and B were the right angles, you'd have 90 plus 90, which is 180, and you have nothing left over to put in angle C, because you would surpass the 180 degrees, okay? So you cannot have more than one right angle in a triangle. And if you did have a right angle, we call those a right triangle, okay? So a right triangle has one right angle, okay? Similar argument can be used for obtuse angles, right? I can't have two angles greater than 90 because just by themselves I would surpass the 180 limit. Okay, so an obtuse triangle has one obtuse angle. You can still have one, but you can't have two or three obtuse angles. Finally, with an acute angle, you can have three angles here that are all less than 90. For instance, you could have a 30, a 60, a 30, a 70, and an 80. That would work. As long as they together equal 180, okay? Any triangle that has all three acute angles is called an acute triangle. So, there it is. An acute triangle has all three acute angles, okay? Now, in a right triangle, you're going to have a right angle and two acute angles. In an obtuse, you have an obtuse angle and two acute angles. So you always have at least two acute angles. But in an acute triangle, you have all three of them acute. Okay, okay, so then we're going to talk about congruent triangles. Okay, so we're going to start comparing more than one triangle. So in congruent triangles, all the corresponding parts are congruent. That's kind of the definition. So if I had two triangles where all of the angles are the same, I'm doing similar here. Where all the angles are the same and all the sides are the same. Of course, these aren't perfect, but they're close. So if I had angles A, B, and C, and angles, I should probably draw that farther away. Let's call these D, E, and F. So those are my 6 angles. And then the corresponding, or the opposite side of each angle we'll call, we'll use those lowercase letters. So opposite angle A is little a for the side, little b, little c, little d, little e, and little f. That's a common way to represent sides and angles on a triangle. So what's interesting then is that the corresponding parts are always congruent. Okay, so corresponding parts of congruent triangles are always congruent. Okay, so for instance, angle B is congruent to angle E. Okay, those are the corresponding parts. Side A and side D are congruent. We'd just say they're equal in length. Okay, so A is equal to D. So all the corresponding angles, all the corresponding sides would be congruent or equal in congruent triangles. Okay. Similar triangles have the corresponding angles congruent, but not the sides. Okay, so in similar triangles have corresponding angles that are congruent. Okay, so if I were to draw similar triangles, maybe here's a smaller one, and here's a bit bigger one. And let's assume they're similar. That just means that the angles are the same. So if I have angles A, B, and C here, then they'd be the same angles on the other triangle. Now the opposite sides are not necessarily the same. Okay. Actually, I probably shouldn't say A, B, C. I should probably go D, E, F. Again. Yeah, let's do it that way. But then we can say that angle A and angle D, because they're corresponding angles, they're congruent. Angle B and angle E are congruent, and angle C and angle F are congruent. Now, if I were to label the sides in the same way I did with the last example, actually, I'm going to switch colors here. Let's go side A, B, C, and then D, E, and F. So the sides are clearly not the same, right? One has smaller sides than the other one. But what's interesting is that they all relate to each other by the same factor. So for instance, if F is twice as long as C, then D would be twice as long as A, and E would be twice as long as B. They're all scaled by the same factor. And for that reason, if you divide corresponding sides, you'll get the same number every time. So if F were twice the length of C, then F over C is 2. And all those corresponding ratios are the same. Okay, so we can come up with a theorem here. It says that in similar triangles, the ratios of corresponding sides are always equal. All right. So an example would be maybe F divided by C is equal to D divided by A, which is equal to E divided by B, up B. All right, so just so you can notice here that I wrote corresponding sides within each fraction, right? So F over C is the same as D over A, which is the same as E over B. Okay, and so this is a relationship that's going to be very important as we move throughout the course.